Hello, friends. Welcome to Science Talk. I'm your host and resident oceanographer, Jim Massa. Okay, I want to discuss with you, and I'm just going to give you an overview of what this paper uh, is communicating. Poleward ocean heat transports, sea ice processes, Arctic sea ice variability in the NOR ESM 1M simulations. And this is a paper that was published back in March of 2014, but it's like everything else in science. We build on what's been done in the past, and this paper contains important information. Results from this model coupled climate model were used to examine relationships between Arctic sea ice area and ocean heat transport through the primary Arctic gateways. Comparisons were made with two other models, they're listed there, that are part of the CMIP-5 archive, which have the required outputs for calculating ocean heat transports. Based on evaluation, NOR ESM1M was found to be the best suited to study the effects of heat transport on sea ice area, and conclusions are based on results from this model. They go on to say, how they divided up the Arctic Ocean, the Barents Sea, the Central Arctic Ocean. Sea ice variability was further analyzed in terms of frazzle and congelation growth. Okay, top and bottom melting. What is frazzle? When sea ice first starts forming, the first hint we get that the ice is forming is what's called grease ice or greasy ice, and as the name implies, it's kind of greasy. The greasy ice then proceeds into frazzle ice, where we start seeing some distinctive shapes forming. It's still very translucent. Still a lot of breaks, and water is there. Then the frazzle ice will start freeze into further. It starts getting a little thicker, a little larger in sections here, and what's called pancake ice. And as the name implies, it kind of looks like a bunch of pancakes floating on the ice, and then that further grows into full sheets covering the water. So basically, frazzle ice is the second stage after the grease ice as we go on to forming sea ice. Congelation, think of congealing. So this is the frazzle ice growing into larger pancake ice, growing into the sheet ice, or congealing into those stages. So that's what they looked at, top and bottom. They looked at heat transports in the Barents Sea opening, the BSO, and the Fram Strait, the FS. In the Barents Sea, increased heat transport in the BSO has a strong influence on sea ice area in terms of reduced congelation growth, while bottom melting is important for the variability in the Central Arctic Ocean. In other words, we have the intrusion of North Atlantic water. It carries heat. That heat diffuses from below to melt the ice from below. That's what's meant by bottom melting. You're melting the ice from the bottom. The top melting will be more atmospheric in source. The negative trend in sea ice area is considerably greater in the Barents Sea than in the Central Arctic Ocean, despite the Central Arctic Ocean area being much larger, and reflects the major trend in the Barents Sea opening heat transport. The model results in this study suggest that the ocean has stronger direct impact on changes in sea ice mass in terms of freezing and melting than the atmosphere, both in the mean and with respect to variability. That makes sense when you consider how much more heat the oceans have absorbed, plus the specific heat content of water in of itself. So the heating effect from the ocean will be more determinative of what happens to the sea ice than the atmospheric temperatures. And we now know, thanks to, based on the ocean heat content video I uploaded, that the oceans have absorbed well in excess of 200 zettajoules of energy, the great majority of that concentrated in the upper 5 to 700 meters. That heat, as I showed in my sea ice melt video, is primarily responsible for why the Arctic sea ice is disappearing. Okay. The loss in Arctic sea ice has been attributed both to anthropogenic forcing and natural variability. Such variability be with the North Atlantic Oscillation, the Atlantic Multidecadal Oscillation, or Atlantic Multidecadal Variability are doing, as well as the Arctic Oscillation, which then, of course, relates to what the high and low pressure systems in that area around Iceland, the Canary Islands are doing, the wind stress that's imparted to the oceans, and other aspects. Okay, so numerous efforts have been made to find a dominant effect. Most studies conclude that both internal and external forcings are needed to explain the variability in sea ice area, but recent reduction is strongly related to global warming and human influence. And they continue to, give a discussion of some of the of what prior research has done, where new research might be required. Right? The Arctic sea ice area variability reflects changes in poleward ocean heat transports. Okay? Atmospheric ocean heat fluxes, ice albedo, atmospheric circulation, ice export through the Fram Strait. Okay? These are all things that have to be considered when looking at why the Arctic sea ice is changing. These processes may in turn strongly affect the projection through feedback and mechanisms in the climate models. Cause and effect is therefore not straightforward since they have mutual influence. Northward shifts of the polar front and corresponding shifts in the winter ice edge may affect the location and extent of areas with strong heat loss. Increased ocean heat transport can therefore be compensated by cooling in these areas. Alternatively, the strength of the Atlantic inflow reflects the changes in the northern heat loss. Numerous examples of how different atmospheric patterns and associated geostrophic winds correspond to temperature and sea ice anomalies, sea ice advection, increased ocean heat are discussed by Overland et al., Lindsay and Zhang. These studies hypothesize that gradually increasing air temperatures through the last 50 years in tandem with shifts in atmospheric circulation have led to reduced thickness of first-year ice, flushing the thicker ice out of the Arctic basin, increasingly open summer water, increasing absorption of solar radiation, melting the ice, warming the water, positive feedback loop, and promoting the further thinning of first-year ice. And then you have to take into account, what is the Arctic Oscillation? What is the Arctic Dipole doing? Does it push ice out through the Fram Strait or constrain it within the Arctic Ocean? I will, of course, leave the URL in the comments section for those who wish to really do a deep dive on your own. So this table here, and I showed this to you in the sea ice melt video, estimates the poleward heat transport in terawatts, okay, based on various studies. So BSO is the Bering Sea opening. That's the Bering Strait. And this is the Canadian archipelago, Narrow Strait, and Fram Strait. So they look at various studies, and then they do the mean of all these studies. So what do we see here? For the Bering Sea opening, nearly 80 plus or minus 13.4 terawatts. Okay? For the Bering Sea, 5.6 plus or minus 3.2 terawatts, 7.7 plus or minus 7.4 terawatts for the Canadian archipelago, and 30.8, almost 31 plus or minus 20 through the Fram Strait. So why these large variabilities? Well, I showed you in a prior video where there seems to be a a decadal signal, decadal cyclical fluctuation in the heat transporting as well as the volume being transported. And this appears to be tied to what the North Atlantic oscillation is doing as far as the locations of the high and low pressure system and the kind of wind stress that the location and the strength will exert on the water. So that will explain these variabilities. So they go through all the models here, ocean heat transport, right? And seasonal cycle of ocean heat transport, well, we would expect that, that there would be one. What I want to, and again, some methods, I want to do is I want to show you this table here. Table 3 lists the mean change in sea ice mass, kilograms per second, exerted by the different freezing and melting processes as described in section 4. In the Barents Sea, bottom melting causes the highest change in sea ice mass, closely followed by congelation growth. Frazzle growth and top melting are an order of magnitude smaller than the first two. So let's look at that here. Okay, here's the bottom melting. 3.2 times E is 10 to the plus 7. So this is 3.2 times 10 to the 7. Congelation growth, 2.4 times 10 to the 7. Now, if you look at frazzle and top melting, it's 10 to the 6. There's your one order of magnitude less. Okay. So the bottom melting is referencing the intrusion of this Atlantic water. Because it's denser, it goes to intermediate depths, and then from intermediate depths, the heat diffuses upward, melts the ice from below, hence bottom melting. Okay, I want to show you this figure here. This is an important figure, okay? And time series of heat transport in terawatts in the top left, BSO, top right, Fram Strait. Okay? And sea ice area given in million square kilometers in the bottom left, Barents Sea, bottom right, Central Arctic Ocean. Note that the scales and the vertical axes are different. So let me enlarge this a little bit. So let's look at the heat transport. This is in time of years. So starting from like 1947 going up to 07. Okay. Heat transport in terawatts. Okay. So we have a baseline. Clearly see the cyclical aspect of perhaps forcings from the NAO. So it is a cyclical aspect, but then we see this increased warming that is greater than any of the other terawatt. In other words, this heat transport has the highest terawatt, and that's occurring in the last several years. When you look at the slope here, it is not zero. So it tells you there's a positive correlation there. And we see heat transport. This is the Fram Strait. We also see that this is also high in the last few years, but it does appear to equal prior high transports of heat. Now, this is the Central Arctic Ocean. The Fram Strait, kind of the boundary between getting to the Arctic Ocean and North Atlantic. So this is not a surprising result to see the influence of the Atlantic and the Arctic meeting and moderating the temperature and the heat transport. We have this low spot here where the heat transport was actually below baseline. And by the way, all these red, these are the errors associated with it, plus or minus 2 standard deviations. But again, if you look at the line here, there is a positive slope. Now, this is where it gets interesting. Sea ice area in square kilometers, millions of square kilometers. We see a clear, especially in the Central Arctic, a clear decline. And we notice how it's picking up in the last several years. So here there was some Arctic gain, some sea ice gain, and we got some loss here. 70s were kind of a cold decade. A lot of strong La Niñas, and the NAO was in, I think, a very negative phase here. But you note, especially in the French Strait, there's a lot of big error here. So what this is telling me, looking at this, is that we see a correlation of increased heat, and that results in decreased sea ice extent. That's basically the take-home message from looking at these panels. Figure 4. Let's look at Figure 4 here. Figure 4 presents correlation between the BSO and French Strait heat transport, bottom melting. Positive correlation reflects more melting as more heat is transported into the area. The resulting pattern for the BSO is one of positive correlations north of Svalbard and in the East Greenland Current, where sea ice is assumed to be present all year round. That's changing, by the way. Don't forget, this is 2014. Negative correlations in the West Spitsbergen Current and in the southern central parts of the Barents Sea, which are only seasonally covered by sea ice. A similar pattern emerges in Fram Strait heat transport. Significant correlation between linearly detended top, Barents Strait, and the bottom, Fram Strait, Barents Sea, heat transports and bottom melting. Contour shore mean sea ice concentration for the period 1950 to 2005. Okay, so let's see, we can enlarge this a bit. So to give you, lat lons here. So this is the longitude. These are the latitudes here, and basically these are the correlations. So this is positive correlations. This is negative correlations. And as the text just said, positive correlation refers to heat melting the ice from below. The negative, not so much. Figure 4 presents correlations between the BSO and FS heat transports and bottom melting. Positive correlation reflects more bottom melting as more heat is transported into the area. Figure 5, growth of the sea ice. Negative correlations, meaning that more heat transport is equivalent to less freezing, dominate the Arctic Ocean in both cases. Okay, we can clearly see that here. This is positive correlation, this is negative. It's negative. So that means, we just said, there's less freezing. So what these studies are showing is that it's the heat contained in the water that's really impacting the sea ice. That's really the take-home message from this and from these series of videos that I'm doing on this. Yes, the air melts it from above, and then when you get the open water, then the air heats up the upper layers of the water, but there's still the influence of the Atlantic water itself, and also from the Bering side, that impacts the heat content of the Arctic Ocean, melting the ice. Bottom melting is found to be the most important for sea ice area variability in the central Arctic Ocean, while congelation growth shows higher correlation to sea ice area in the Barents Sea. In addition, Figure 4 reveals some interesting results comprising both positive and negative correlation between heat transports and bottom ocean in the central Arctic Ocean and the Barents Sea, respectively. That more heat advected into an area should lead to more bottom melting, as in the central Arctic Ocean. Is not surprising. But more heat transport related to less bottom melting in the Barents Sea, as given by the negative correlation, necessitates further analysis. This can be explained by the sea ice concentration in seasonally covered areas. More heat transport in these areas leads to less freezing by congelation growth, meaning that if there's less freezing, there's no ice to melt later on, and less ice is available to be melted. So therefore, more heat transport gives less congealing growth and less sea ice, and finally less bottom melting. But when you have the ice present in the central Arctic Ocean, then that heat leads to more melting from below. It makes perfect sense. So the result is consistent with a statement in Smidrup in 2013 that most of the ice loss in the Barents Sea ice during winter is not caused by ice that melted, but rather by ice that never formed. Whereas in the central Arctic Ocean, you do have ice there, and so the heat will melt it from below. So you have heat moving in the Barents Sea. That heat prevents the ice from freezing. So therefore, if the ice doesn't form in the first place, the heat's not going to melt ice. You can't melt something that's not there. It's basically what they're saying. So that's an important result. It shows the difference between freezing and melting processes, how that impacts sea ice area. To kind of wrap this up here, the model results argue that increased heat transport in the Barents Sea opening has strong influence on the ice formation in terms of reduced congealing growth, and that this causes reduced sea ice area in the Barents Sea. BSO heat transport also affects the bottom melting in the Barents Sea, but increased heat transport does not yield increased bottom melting in this area because there's no ice to melt. This can be explained by a total sea ice area available to be melted is less. It's reduced due to less sea ice formation. Freezing and melting processes are approximately balanced in the Barents Sea. This is now recent research is indicating that the melting is exceeding the freezing. But remember, this was published in 2014. This is not the case in the Central Arctic Ocean, where congealing growth strongly dominates the other processes in changing the sea ice mass, while bottom melting is more important for this variability of the sea ice area. Lastly, this study suggests that the ocean has stronger direct impact on changes in sea ice mass in terms of freezing and melting and in area and in volume than the atmosphere does. So, summary. More heat is being moved into the Arctic Ocean, especially through the Barents Sea. The Barents Sea heat helps prevent the freezing of the ice to begin with. That heat continues moving into the Central Arctic Ocean, where that heat now melts the existing ice from below. And we also have contributions through the Fram Strait. Heat content of the water is more influential in what happens with the sea ice than the atmosphere. And we now know that the oceans have been absorbing a shitload of a lot of energy. 93% of greenhouse gas emissions have been absorbed by the ocean. And that heat is what's driving a lot of the sea ice melt. That's basically what's going on. And we are headed, now we can fast forward to 2021, we are headed to a blue ocean event that may become permanent within 10, 15 years or so, plus or minus. So as we continue to warm the ocean, this ocean heat makes its way into the Arctic Ocean, affecting the sea ice. I've shown you now a couple of studies that basically arrive at similar findings and conclusions, namely that it's more the ocean than the atmosphere. The atmosphere does play a role on the top side, if you will, but it's really what the oceans are doing, the heat they contain. And not only the heat, but the volume that moves in. If you have more volume moving in, that can bring in more heat, having more of a melting effect. So it's heat, increasing heat content of the water, increasing flow rate. Now, in these, we do see a decadal oscillation, but recent trends of the past 10, 20 years show that the anthropogenic effects are now becoming more of an impact than any natural variations. And that's part of what we do. We differentiate the signals, the contributions from natural variability and human-induced. So, and the trend is that the warming is due to human activity, and this is helping to drive the accelerating loss of the sea ice. Again, I will leave the URL in the comments section for those who wish to read this paper in detail. But that was the main message that I want to bring to you, and give you further general overview of what's happening to the sea ice in the Arctic Ocean. Thank you for your time. Hello, folks. This is Jim here with Science Talk. asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.